This is podcast number 35. And this week we're going to start talking about how organisms convert energy from one form into another. This is a form of homeostasis. Homeostasis is one of the big ideas of biology. First, we've talked about it a little bit when we talked about the properties of life, how viruses don't really do homeostasis, but all other things that we consider alive do. And we are on chapter 10 here. You're going to revisit this in 11 and 12 this week, and then again in Principles 2. So one way to think about homeostasis is like a thermostat in your house. So if you take temperatures at your thermostat, and then you take temperatures in different rooms in your house, it's not that they don't change. They do change, but they change over a relatively narrow window. They're not swinging all the way really hot. They're not swinging really cold. They're maintaining within a certain range. And that's one way you can think about homeostasis for cells, is that they're maintaining internal conditions within a range of acceptable extremes. You regulate the pH of your blood. You regulate the pH of your stomach. You regulate how much glucose is in your blood. You regulate how much cyclic AMP is in your cells. All those are examples of homeostasis. So you'll see this as we talk about these things this week. You'll see these ideas coming through. Biological systems use feedback to maintain optimal conditions. So a thermostat has an electrical coupling that has two pieces of metal that change their expansion or contraction based on the temperature, and they open or close the circuit based on that. So they're using feedback. In a thermostat, feedback is the temperature of the room to either add heat to the room or to shut off. Time-dependent processes regulate biological systems. Life requires organization, which is energy-dependent. Size and environment shape response to physical and chemical challenges. These are all things that we'll see as we talk about homeostasis this week. So, in talking about how energy is converted by living organisms, you're introduced to laws of thermodynamics. These are things that that are very predictable and seem to be true in all cases. One of them is the first law of thermodynamics, in that energy can be neither created nor destroyed. It's just converted from one form to another. So if we think about corn, you have corn in the plant, and then converting that chemical bond energy in the plant to corn, the vegetable that we think about, and then corn, the seed, which turns back into a plant. So these are different forms of energy, and it's not that this has the same energy as this, which has the same energy as this, but it will exchange energy with its environment and change form energy. It'll give off some of that energy as heat, some of that energy as light. Some will be captured as chemical bond energy, such as in the glucose molecules of the corn, which the corn seed uses to start growing the small corn plant. And then later we'll talk about how photosynthesis harvests sunlight energy and CO2 from the atmosphere to fix carbon into place and so on. But the energy in the total system in the universe is constant. It's not, you don't create energy, you don't destroy energy, but you can convert energy into one form or the other. Heat versus light, for example. Heat energy can do work. Here's some heat energy being released from the carbohydrates in the wood by burning. That creates heat energy, also creates light energy. Some of that energy is transferred to the pot, and then some of that energy is transferred to the water, causing the water to boil. Some of that energy is going to be given off into the atmosphere. Some of that energy is going to make like ash. This reaction of converting heat into steam or liquid water, we take advantage of that in power plants. So this power plant is burning coal to boil water, which makes steam, and steam is used to move a turbine, which is a coiled piece of wire that's going to move in a magnetic field, and that'll generate electricity. But originally the energy came from heat, converting it into a different form here, electricity. You can measure the transfer of energy from one place to another. It's not efficient in the sense that all of the energy in that wood is not transmitted to the water. Some is released into the atmosphere, some goes to making light in the flame. So not all, if you looked at the total energy that is in the wood, not all of that energy is available to do work. The portion of energy that's available to do work we call G. And then there's also this idea that randomness of the molecules, their position in space and their motion, that's called entropy, or S. And that is the basis for the second law of thermodynamics, in that entropy, which is the amount of disorder in the universe, always increases, always increases. If there's a temporary decrease in disorder, like putting two molecules together in a covalent bond, that's always temporary, and it's accompanied by a bigger increase in disorder. So even if you have a small decrease in entropy, it's at the same time you have someplace else in the system, you have a bigger increase in entropy, so that entropy in sum is always increasing. So you can put these into an equation which sort of looks like the word ghost. Delta G. Delta is a capital Greek letter. Looks like a triangle. If you're in a fraternity or a sorority, you might have a delta in your fraternity or sorority name. That's a capital Greek letter delta, and in science is used to mean change. So change in work energy or free energy equals the total change in energy, which is H, minus the change in entropy times temperature. So the energy available to do work is equal to the total energy minus the energy from entropy, due to entropy. So if we look at a molecule and you say, where is the energy in a molecule? Because cells are going to be dealing with molecules. You've already seen this molecule before. This is ATP. So here is the sugar. Here's the 3 phosphates, and here's the base. Over here, the energy is in these covalent bonds linking these 3 phosphates, or in linking these carbons, etc. That's where the energy is. And all covalent bonds don't have the same energy. It all depends on what it's holding together. In this case, these two phosphates have negative groups on the outside. This is negative on the outside. And two negative things tend to repel each other. And so there is a fair bit of energy holding that bond together. Having said that, and recognizing that all covalent bonds don't have the same energy, sometimes that particular bond right there is called a high energy bond. There's nothing necessarily high energy about it. It's just relatively easy to break. So even though there are bonds that differ in the amount of energy that is in them, even though they're all covalent bonds, and even though it's difficult to hold two negative charges together like that, that is not necessarily a high energy bond or specifically high energy, but it is relatively easy to break. You put strain on that molecule there, these two things are going to want to come apart from each other, and it's relatively easy to break. Okay? Those are those three phosphates right there. And then a phosphodiester linkage to the nucleotide. So when we were talking about these chemical reactions, which we'll talk about this week, we'll talk about how much free energy is in that reaction. So when I break a bond in a biological molecule, how much energy is available to do work for the cell, how much free energy is available. And you can measure that with a couple devices. This thing here is called a bomb calorimeter. And you can put a biological compound like sugar, for example, inside this chamber. There'll be a spark that starts this chamber burning. It's in an oxygen atmosphere, and it'll burn to completion till all the sugar is gone and it's just char remain. And that burning will release heat, and the change in water temperature that is surrounding that temperature will measure how much heat is produced by the reaction. And that's where you can get H. In that GOST equation, that's where you can get H. Okay? To measure G, to get to delta G, you can use another sort of chamber. In this sort of chamber, you typically put two what are called redox reactions. So in one side of the cell, something is being oxidized. In another part of the cell, something is being reduced. And it could be either side. Traditionally, hydrogen is being oxidized over here, and then whatever you're interested in measuring, some biological molecule like glucose, for example, that's put over here. And the oxygens from hydrogen would be removed in an oxidation reactions and then added over here in a reduction reaction. Like that. You can measure the electrons moving out of this chamber and into this chamber with a voltmeter. And electrons moving is typical of the sort of thing that is going to happen inside of a cell. And so this is an approximation of how much work energy is released when these reactions happen inside a cell. This is a chem lab sort of experiment, but it's trying to get at that question. Now, I mentioned oxidation and reduction. We're going to talk about how glucose is oxidized, how fatty acids are oxidized, how amino acids are oxidized. And you can remember this little phrase, oil rig. So oxidation is loss. So in this chamber, electrons are leaving. You're losing electrons, and therefore it is being oxidized. Okay? And reduction is gain. This side over here is gaining electrons. This compound over here is being reduced. So they list both here because you can put either one on either side. But in this example, R1 is being oxidized and R2 is being reduced. So people get confused about this because you're adding to something and you're reducing it. What you're doing is you're reducing the charge. It's getting more negative as you add electrons. So oxidation is loss, reduction is gain. Oil rig, remember that one. Okay, so ATP and also GTP have evolved as molecules that are relatively easy to oxidize and release energy that can be used to do work by cells. So this ATP molecule converts to an ADP molecule by removing that last phosphate, and it'll release energy. And you do that thousands and thousands and thousands, millions and trillions of times a day. You do that reaction inside your cell. And in fact, the average person, say, I'm average, probably I'm below average in terms of size, but I weigh 153 pounds. I'm 5 feet 6 tall. I'd say I go through 2,000 calories in a day. I'm going to burn through 500 pounds of this stuff, ATP, and convert it into ADP in a day. Obviously, I don't weigh 500 pounds. Well, you haven't seen me, but take my word for it. I don't weigh 500 pounds. So the reverse reaction is happening all the time too, where that phosphate is being put back on ATP. But to release energy, that ATP is released to ADP plus P, all over and over and over again. And if you just measured how much ATP got converted to ADP in a day, in somebody my size, it's about 500 pounds. So it's a very, very common reaction, probably the most common chemical reaction that's going to release energy that cells can use to do work, or delta G. Okay? And 32 kilojoules per mole, that's a number. The numbers doesn't mean much to you now, but in a second we're going to think about these units and try to get an idea of how they compare to each other. So delta G is what we're after, okay? And delta G is in joules, which is a unit of heat, per coulomb, or moles of electrons per mole of reaction, or coulombs per mole of electrons. If we do the dimensional analysis, we can get that to joules of heat released per mole of reaction, and we can measure different reactions that are common inside a cell. So there's an online electrochemical cell that you can plug this stuff into, and you can do these calculations. And we're going to look at these molecules. Some might be familiar to you, or some might not be familiar to you to begin with. But some molecules have more energy, potential energy in them, in terms of if you put them in a delta G measuring machine with a voltmeter, like I showed you earlier. Some will release a lot more electrons that are possible to do energy reactions with, and some less. So glucose is the champion on this list. It releases a lot of energy per mole, and a mole is just a unit of stuff. like a bushel or a peck. And a mole is 6.02 times 10 to the 23rd molecules. So if I have 6.02 times 10 to the 23rd individual glucose units, and I get all the electrons I can get out of them, they will release 2884 kilojoules per mole. And then pyruvate, which is half a glucose, releases about half the amount of stuff, not quite half the amount of stuff, because it's not a perfect reaction. You're going to lose some energy. Is going to be wasted as heat as you go through those different reactions that we're going to talk about. And then the oxygen is going to get added to hydrogen at the end of one of these reactions, and that's going to release a certain amount of energy. And then there's a electron carrier called NADH that when it releases its electron, it's going to release a certain amount of energy. And there's another type of electron carrier that when it releases its bound up electrons, it's going to release a certain amount of energy. And then ATP can also release a certain amount of energy. So these are molecules that we're going to run into when we talk about glycolysis. And you're going to see what's going to happen is we're going to start with glucose. Glucose is going to get oxidized through a series of reactions. And what the cell is going to do is just take off a little bit of electron step by step by step, and to get the most energy we can possibly get out of that glucose and energy that can be used to do work, delta G. One more thing, you notice that the numbers on all of these delta G's are negative. A negative delta G means that the change in energy is you end up with less at the end of the reaction than you started with. Okay, so glucose had a lot of energy in it. When I convert it to all this stuff by breaking it down, I have that much less energy in all this stuff than I did in glucose when I started. So this amount of energy is released because the amount you end up with is less than what you started with. The difference between what you started with and what you end up with is the energy that's available to do work. And if it has a negative sign in front of it, that means that this reaction will proceed spontaneously. If you get the reaction going, it'll go all the way to completion on its own. If there is not a negative sign in front of this, that means that the reaction is not spontaneous, and you have to add energy in order for the reaction to happen. That would mean that the stuff on this side of the equation had more energy in it than the stuff on that side of the equation. And so if I start with this, I would have to add energy in order to get that, and that would be positive. But if the stuff on this side of the equation has less energy than the stuff on this side of the equation, I release energy when I go from here to here, and that's why it's negative.